much. Very excited to be back. Of course, it would have been better even in person, but I guess that's the current state. I'm going to talk about a preprint that I wrote together with Nick Jones and Michael Schaub. All of the code for our project is available on GitHub, and it's written in a mixture between Mathematica and MATLAB. Specifically, MATLAB is used for numerical optimizations, where Mathematica can be used for some of the analytical or semi-analytical optimization I'm talk about. Yeah, and I should say what I'm going to talk about is how to define modularity for graphons. I'm first going to talk a bit more generally what graphons are, and then why we would be interested in computing something like modularity for graphons, and then I'm going to talk through our results. So as most of you are probably aware, a graph is a selection of vertices and edges. Here we are going to talk about binary undirected edges. So in this case, you can write the adjacency matrix as a symmetric binary matrix in which you have ones indicating if there's an edge between a pair of nodes and 0 if there's no edge between a pair of nodes. And now you can ask the question, if you have a very large graph, is there any way to approximate such a discrete structure, which is an adjacency matrix, with a continuous mathematical structure? And this is exactly what a graphon is. Something more specific we have in mind is, for example, if you have this adjacency matrix and you have a growing graph. So you have a sequence of graphs where you always add a node and you connect edges with some kind of iterative way. So for example, you can think of a Barabasi-Albert model. This is a slightly different variant called the Gruen uniform attachment graph. But again, you can think of something similar. If you then go to very large node sizes, the kind of pixel which indicates the entry of each entry in the matrix gets smaller and smaller. And so you approximate to some kind of continuous object. So of course, this is still a discrete object because each pixel is discrete, but it kind of becomes looking like an almost something continuous. And this is exactly the graphon. So it's a continuous limiting object for infinite size dense graphs. So again, you have this pixel image, and then for large sizes, you see that it's going to approximate, it becomes similar visually to such a graphon, which is the infinite side limit. There's a lot
Can I super quickly interrupt, Flo?
Of course.
There's a lot of background noise from your microphone. I don't know if...
On my, or maybe I'll just hold it like this. Okay.
I think it's rubbing against your shirt.
Okay. Okay. Thank you.
Sorry about that.
So yeah, this graphon is kind of like a continuous limit of such discrete graphs. There's a lot of theory behind this, how we can actually prove this convergence of such a sequence of graphs to the graphon. And most of this work has been done by Borgs and Jennifer Chase, for example, in this paper, but there are also other accompanying papers. And in this example here, for example, the graphon that we actually get is a function that looks like this, 1 minus the maximum of x and y. And x and y are the positions here along those along this image. So the graph is a symmetric measurable function from the unit square to the unit interval 0, 1. So what we mean by this that we take the square and each of the positions is then getting assigned one value between 0 and 1. And this value is some kind of measure of the density of edges in the infinite size case of nodes that would be there positioned. So this is kind of like the graph theoretical view on graphons. They become more and more now used also on the applied side because they can be interpreted as a non-parametric random graph model. So as I said earlier, the graphon is a symmetric measurable function, and you can interpret the position of this under the unit square as the connection density or the connection probability at position x, y. And now we can construct a graph from a graphon by sampling. So, and we do this in a procedure where for each node, we sample position between 0 and 1. And then we connect those nodes with the probability which is given by the Wxy xj. So for example, if you have now a position here, and two nodes are then connected with very low probability, whereas if they would be here and here, they would be connected with a high probability. And so this is just the adjacency matrix element that you can sample. So it sounds a bit abstract, but actually graphons encapsulate a wide range of existing graph models. So for example, the simplest case would be an average linear graph, where the graphon is just constant p. So independent of the position of the nodes, the connection probability between a pair of nodes is just p. Then another example is stochastic block models. Specifically here, I show a planted partition model, where if nodes are close by each other, so they're in the same group, then you have the connection probability p internal, whereas across group borders, you get the connection probability p out. Another example is in bipartite networks, where you have actually kind of like the opposite case of the planted partition model. If two nodes are close by in position space, they won't be connected, whereas if they're far apart, they're actually connected with probability 1. So that's now a complete bipartite network. But there are countless of further examples where it's not as easy to draw a graphon picture. For example, there's random dot product graphs, latent space models, similarity kernels. So overall, it's a very flexible probabilistic graph model. However, it also has some caveats. So one thing to keep in mind is that those graphons are usually only unique up to measure preserving bijection. What we mean by this is that if you take this image here of the bipartite network, you can actually realign the positioning of the nodes in a different way, where you get such a chessboard. And it actually is exactly the same probabilistic graph model. It's just a reordering of the node positions. So this is essentially equivalent to a relabeling or a reordering of vertices in a graph. So whenever we have such a kind of like pretty graphon picture in mind, we have to be aware that it is only unique up to this measure preserving bijection of the space. So what kind of research is going on in the domain of graphons? So specifically in the applied field, one thing is, for example, centrality measures, where my co-author Michael Schaub wrote a paper. And specifically, it's something we're going to use later is the definition for the degree. But they also define, for example, eigenvector centrality. So if you have the degree of each node, since the nodes are now defined in the space from 0 to 1, we can define the degree of each node position just as the integral over the graphon function. And here I have an example. So that's the same. It's again this max graphon we talked about earlier. And the solid line is the graphon degree, which is just a parabola. And then if I create a graph from this, I think this is with size 100, and then I look at the degree or the rescale degree of the nodes in the sampled graph, you're going to see that it closely resembles the graphon degree, but of course not exactly, because there are always going to be some random fluctuations. But for example, if you would now create a sample which is very, very large, so for example, 100,000 nodes sampled from this graphon, then it's going to be very, 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 very closely follow the graphon degree, as the solid line shows. There's further research going on, for example, about dynamical processes on graphons. Kuramoto model has been generalized to graphons, and Renault actually worked on random walks and the Laplacian function for graphons. Gesine here from the University of Oxford has also one paper on subgraph counts, and subgraph counts are important in the whole graphon paradigm because they're one way of showing convergence of graph sequences to graphons. And one other field which is has a lot of research going on in the computational literature is the graphon estimation. So that's the question of to what extent, if you have a graph, can you reconstruct the graphon it was sampled from? We're going to talk about this a bit more later because it's relevant for some of our results. Okay, and so now where we contribute is that we define this community detections in graphons. So as I said earlier, if we have some kind of graphon, we can generate a network from this by sampling this. And usually, if we think about community detection, we think about community detections in graphs. So for example, then you have a network and you want to infer the community structure of this network. So what we mean by this is that there's some kind of partitioning of the nodes that is optimal in some kind of way that it, for example, minimizes the edges across community boundaries. And now what we wanted to answer in our work is the question whether we can define a similar community structure for graphons. And then also we want to look at the community structure from the graphon and compare it with the community structure in the graph sampled from the graphon, and to what extent they are similar. And there are a couple of further motivations which I want to talk about. So first of all, under which conditions do graphons have a community structure at all? Then something we figured out kind of like while we worked on this project is that the continuous functional form of a graphon can be used to define some kind of continuous optimization problem, which is basically a fresh view on the community detection problem. Something we also found is that the graphon estimation as an intermediary step may improve the community detection on the network. And lastly, we want to argue that this community detection on graphons is actually also a privacy-conserving computation of community detection in a network. I'm going to touch about all those motivations throughout my talk to make them a bit more clear. Yeah, so what is the definition of community detection and graphs on graphons in general? So for a graph, it's finding an optimal partition from the set of vertices to the labeled communities. So we have discrete communities, non-overlapping. So we label the communities from 1 to C. And now graphon is the equivalent problem, but it's finding an optimal function from 0, 1 also to discrete communities. So keep in mind, while the interval from 0 to 1 is now continuous, the communities are still discrete. So usually there are many different ways to find such an optimal partition for graphs. One of the most widely used ones is modularity, which probably most of you are aware, but I'm going to very briefly talk about it. So if we have given a partition, how do we define the modularity? We count over all pairs of nodes, and we only count them if the two nodes are in the same community. And what we sum up is the adjacency matrix elements. So this again is 1 if there's a no edge and 0 if there isn't. And we have to subtract some kind of null model, which is the expected connection strength. Most widely used is just the product of the degrees of the two nodes divided by the number of edges. So if you have this partition here, we sum all nodes that are inside of the communities, and we subtract some kind of estimated null model where we again only count the nodes, the edges that are inside of communities. As you probably are aware, if this is defined for one partition, what we usually want to do is we want to find the partition that maximizes this modularity among all partitions, which is a NP-hard problem. So you have to do some kind of heuristic to optimize this. Most widely used is probably nowadays the Levong or Leiden algorithm, in its, which is the updated form. And so it tries to find some kind of optimal partition, or at least close to optimal partition for the forms of this modularity. And now we come to the modularity for graphons. It is actually very similarly defined. Essentially, what we do is that we replace the discrete sum over all pair of edges with a double integral over the, or integral just over the square. And then we replace the adjacency matrix with the graphon function, and we have to define some kind of new null model. You can use any null model that you find appropriate for your application. We decided to use something that is close to this Newman-Girvan type null model. So it is the degree of each node times the degree of the other nodes and divided by the total number of edges. So the picture we have in mind, if you have some partition here of your graphon, you count basically, or you sum, you integrate over those squares that are inside of each community. But then again, you have to subtract some kind of normalized null model where you again count inside of each community. Similar to the graphon, the problem is that this is now just for a given community or for a given partition. And the question is, how can we optimize this partition in any way? And we use two different approaches, which have different advantages and disadvantages. In general, they seem to provide very similar results in the graphons we tested. The first is that we can discretize the graphon. So what this means is we have this modularity surface. So this is this graphon function minus the null model. And so we can now just create a grid from this. And then we can assign each of those grid points initially a random assignment to a community. And then we can apply the Jen-Louvain optimization algorithm, which is a Louvain implementation for MATLAB by Lucas Joip, Maria Bazzi, and others. And you can optimize for each of those little slivers, or each of the slices of the interval between 0 and 1. You can optimize this partition, the function, which assigns each of those positions to a different community. This, of course, has the disadvantage that we kind of take our nice continuous object and approximate by discrete stepwise functions. However, you can actually do this very high resolution. So we usually choose a 2002 times 2000 grid. And even if you go to higher grids, you still get the same result, essentially. A second approach is where you actually can directly use the continuous functional structure of the graphon to optimize the partition. And so what we often find in at least synthetic graphons is that the community structure looks like this, that you have basically continuous communities, and that you have some kind of border, and then the next community starts. So that is in contrast to here, where you have one community, second community, and then again the first community. And so if you assume this continuous structure of the communities, what you actually can do is you can simplify this modularity function to just a sum of something we call sliced modularities. So essentially you have only this square, and then the only thing you have to optimize is the positioning between those communities. And this, of course, reduces the number of free parameters to C-1, where C is the number of communities you have. I should say you can also make this more complicated and allow such non-contiguous communities as here, but then some of the advantage disappears because it's not as nicely optimized anymore.
Florian, can I just ask?
Yeah,
so usually when you do community detection, one of the big issues is to relabel the nodes, right?
Mm-hmm.
And so here in this framework, is there also a relabeling that is done once you've been doing the discretization, for instance?
Yeah, you can do some relabeling after you have applied, for example, the Louvain algorithm. Mm-hmm. Here in the continuous optimization, I have to admit we haven't found a nice way of doing some kind of automated relabeling. And I should say that this continuous optimization usually seems to work only, at least in our case, only for synthetic graphons, where you have basically essentially the ordering given.
Okay, thanks.
Yeah. So basically the continuous optimization has some allows for synthetic graphon proving the optimal community structure, and the discrete graphon is to some extent slower and less nice, but it's more versatile. So for example, it can be applied to graphons estimated from some kind of empirical data, because then it's usually given in a discretized form anyways. So for the first example, I'm going to talk about something which is a core periphery model. So it has the functional form of Wxy is 1 minus lambda xy plus lambda, and lambda is a free parameter and 0, 1. So this essentially, you have this choroperiphery structure, and then you have this lambda as an offset, which is like a mixing parameter. So the example here we have for lambda equal like 0.2, the graphon looks like this, and the degree is a linear increasing function. And if you compute this modularity surface, we here highlight the positive parts with red and the negative parts with blue. And what you find is that you essentially already can see here that there's one part of the graphon which is here assortative. So nodes close by to each other are more connected than you would expect under the random null model. And similar here, you have a second part where the nodes are more connected to each other than you would expect under a random null model. Whereas the connection between those two groups is less than you would expect at random. That's why it's negative. And if we use the Jen-Louvain algorithm to optimize this discretized modularity surface, we return those two communities which represent those two parts which are densely connected to each other. And actually the split between those communities is exactly at 0.5. The nice thing about this graphon, that's why we choose it as first example, is that you can compute the modularity surface analytically. And also, if we now use our approach with the continuous optimization, so we assume that the communities just consist of two communities which have one border position, which is kind of verified because we got the result from our discretized approach. If we assume this, then we can actually get also a closed form solution for the modularity as a function of lambda, which is a free parameter, and x1, which is this border between the two communities. And if you optimize this function, you find that the maximum is exactly at 0.5, as long as lambda is not 0 or 1. Actually, for the case that lambda is 0 or lambda of 1, you don't find any communities, which we can also prove, which I'm going to talk later about if we find the time. Another example, which I used at the beginning as illustrating example, is this max graphon, which is the limiting object for this growing uniform attachment graph. Here, the graphon, as we talked about earlier, looked like this. The degree function is this parabola. And now if we look at this modularity surface, we find that it's kind of like assortative along the diagonal, but it's not entirely clear what would be the optimal modularity just from looking at this modularity surface. If you use the Jen-Louvain algorithm, then we find actually three communities. You have the first community, which is the high degree nodes. So this is this part. Then you have a second small community with the intermediary degree nodes here. And then you have the largest community, which has all the low degree nodes together. We can again compute the modularity surface analytically. However, we can actually not minimize this analytically. However, what we can use is some kind of continuous optimization procedure. So for example, Mathematica, and what we find is actually this continuous optimization approach, which again has only two parameters, this x1, which is the border between one and second community, and x2 between second and third, that this result is actually very similar. I mean, it's not absolutely identical, but up to essentially just the discretization of the modularity surface up to this, it is the same. Something also I should highlight that, of course, you don't always know the number of communities, what we kind of used for this sliced approach. However, if you, for example, now introduce additional communities, so for example, here we tested it up to 5, then actually the additional communities just collapse. So for example, if you would have 3 and 4 as additional community borders, they would go to 0 and 1, essentially giving the same community structure. Then another very widely used graphon, as I talked about earlier, is the planted partition graphon, where we essentially know which partition we want to expect from this graphon. So you have those, in this case, 3 communities where the connection is high inside of the communities and low across community borders. The degree is the same for all nodes here. And the modularity surface which we obtain is positive inside of each community and negative across communities. And as expected, if you apply the Lovon algorithm to this graphon, we exactly recover the communities as planted. And so actually, since the modularity surface is always positive inside of the planted communities, but negative across, there's no detection threshold. So this means as long as P internal is greater than P external, we're always going to exactly recover the planted partitions in this graphons. However, as many of you might be aware, there is actually a detection threshold if you have a graph sampled from planted partition model. So while the sampled graphs will undergo detection threshold, the graphon itself will not undergo the threshold. So now we wanted to explore this a bit further, this kind of notion about to what extent is there a detectability threshold. And so what we did is we take a graphon, so actually a planted partition graphon, where we know the community structure we expect. We generate a network from this, and then we do a community detection on this network. So that's what I highlight here with A. But also what we do is we take the network, we estimate the graphon back from the network that we sampled, and then do community detection on those estimated graphon. And we're going to compare the community structures from this graphon with the planted and from the graph with the planted. So as I said, we do this for this planted partition model. So we compute the adjusted mutual information index. So higher values mean it's in better agreement with the planted partition, whereas lower is in worse agreement. And here on the horizontal axis, we have varying external connection probabilities. So the case with P external being 0 is that you have a very strong community structure, whereas 0.05 is the same as P internal. So there you essentially have an Erdős-Renyi graph. So you have actually no community structure. And the case in between is where you have a weak community structure, which is usually what you're going to have in reality. And the three colors are three different graphs, so sample sizes. And then let's first look at the sampled graph. So that's the dashed line. So what you see for all three sizes is that if the community structure is very, very strong, then we perfectly recover in our planted, in the graph, the planted partition. However, if the community structure is weak, or actually if there's none at all, we cannot recover the planted partition. And now to our surprise, what we actually found is that if you have this estimated graphon, so you take the graph, you estimate the graphon, and then you do community detection on the graphon, you actually have a similar behavior. However, in all three cases here, there's a small range of external connection probabilities where the estimated graphon seems to yield a better adjusted mutual information than the sampled graph. So that means that for all of those sample sizes, there's a range where the intermediary step of estimating a graphon can actually improve our connection, our recovery of the planted partitions. There are also some graphons which do not have community structure. And this, for example, happens when the modularity surface vanishes. So that means is that the modularity surface is 0. And that means that the modularity is going to be identical for all graphs, for all partitions. And we actually find that the graphons of the form fx times fy, where f is any integratable function, always do not have community structure. Examples are, for example, the Erdős-Renyi graph, because then wxy is equal to p. So you can then just write it as square root of p times square root of p. And also the core periphery model I talked about earlier, for lambda equals 0, it actually becomes just wxy is equal to x times y. And so this then also this form f of x times f of y. So this explains why in the core periphery model I talked about earlier, for lambda equals 0 and lambda equals 1, we cannot obtain any communities. And for all the other cases, we exactly get these two communities. However, keep in mind again that a graph sampled from a graphon might actually have a community structure. So this is, for example, known for Erdős-Renyi graphs, that if you sample a graph from Erdős-Renyi graph, you're going to have some kind of optimal community structure, which, for example, optimizes the modularity. However, it is usually not statistically significant. then what we wanted to explore is a bit to what extent we can apply this to empirical data. So empirical data is, of course, usually given in a graph format and actually not as a graphon. So what we first have to do is we take a network, we estimate a graph from it, and then we can do the community detection on the graphon. And what we wanted to do is we wanted to compare the partition that we obtain from just optimizing the modularity on the graph with optimizing the modularity of the estimated graphon. Since there's a whole range of different graphon estimators available, we used three very different kinds, because we wanted to show whether there's, for example, an influence of the different graphon estimator into the partitions we obtain. And we find that there's actually quite a strong influence. So again, adjusted mutual information, 1 shows a strong agreement, where 0 is no statistically significant agreement. So there's one graphon estimator, which is called the sort and smooth estimator, and there actually you find that in all of our empirical networks, the adjusted mutual information is very low, so that there is almost no statistically significant resemblance of the graphon community structure with the graph community structure. Then matrix completion approach, you find always kind of like decent agreement, but it also, again, it depends heavily on the graph. So for example, some graphs it's quite low, whereas the Senate voting, which has a very strong modular structure, there we almost perfectly recover the partition. And then there's also something called the universal singular value thresholding approach, where we find it does sometimes very good, so actually best from all of our methods we tested, but also sometimes it fails completely. So this actually happens if this universal singular value thresholding approach does not basically in some cases it says the best graphon we can estimate is just an Erdős-Renyi graph. And so this, for example, happens for the Zachary Karate Club and the Facebook network. And then, of course, it cannot find any community structure, and then the AMI is going to be 0. So this kind of indicates that you can use this USVT approach, and if it gives you a result, it's probably quite decent. Whereas if it doesn't work, then you can use also this matrix completion approach. So the question is a bit, why would we at all be interested in this comparison between empirical data and the actual graph? So because you could argue like, oh, why would I be interested in estimating a graphon if I actually then want to de-estimate the community structure, because I could do it on the graph itself. I mean, on the one side, we have seen earlier that actually this intermediary step of graphon estimation can improve our community structure. And second of all, I want to demonstrate that it also allows a way of privacy conserving computation of community structure in a network. So have in mind that you might have some kind of network and you don't want to share this network with the world because it could be some kind of sensitive data. So it could be some medical records, or could be just a social network, for example, could be a Facebook network, and you don't want to share this with the whole world. However, you need maybe, for example, cloud computing resources. So you kind of have to share some data with an external entity. So what you can do is you can take the network, you can estimate a graphon, and then you can just share the graphon with the world or with the outside entity, whereas you can actually keep the node position. So this is the information to which position in the graphon each of those nodes belongs to. And then you can take the graphon, for example, your cloud computing entity, you can do this community detection in the graphon, you obtain a community structure, and then you got the community structure is returned to you, and then you combine it back with the node positions and actually get the community structure in your graph. And you have not shared individual information about the connectivity of each of those nodes or which individual each node is associated with the outside world. So therefore, it's some kind of paradigm for this private community community detection. And this is especially also interesting because there are some algorithms which allow you the estimation of graphons in a privacy conserving way. So where you don't share the information about the edges with the graphon estimator. Okay, I think I'm going to wrap up now. So I demonstrated or I introduced you that you can graphons use as a limiting object for dense graphs, and there's a rich statistical literature on this. What we then did is we defined a community detection for graphons and demonstrated two different approaches to optimize this modularity function. In some cases, we can actually prove the maximum modularity community structure for synthetic graphons. And if this is not possible, we can always use some kind of numerical approximation. And the graphon estimation as an intermediary step may actually improve the recovery of planted partitions, at least for some range in a stochastic block model. And lastly, I talked about the application to empirical data, where I showed that graphons may allow privacy-conserving community detection. As I said, the code in MATLAB and Mathematica is on GitHub, and the preprint is available in archive.